So for our goal for today, our goals, I guess, is going to be proving the sort of essentially the weekly lower semi-continuity property. And then, I mean, time permits, we're gonna get to the question that I asked you guys last time. Also, I mean, just a quick question, but I mean, you know, I'm skipping first the point about the uniform integrability of gamma k dot. Okay, so we're gonna need to revisit that. That's gonna be quick. Anyhow, that's the goal. So I recall quite quickly the strategy and the setting here. I mean, like we have admissible sets that are containing of curves that are absolutely continuous with two fixed endpoints, y and z. Again, later on, we're gonna deal with curves, you know, mapping from minus infinity to b or something like that, or from a to infinity, but that's for later. For now, we are considering a fixed length interval AB. And the action functional is this. And again, our goals, you might be bored already by now because I keep repeating that our goal is to minimize this action functional over all curved gamma in the admissible set. And I recall the setting that we set last time, that you know, we first show that there exists a constant c so that I of gamma is greater than or equals to minus c for all gamma in I. You know, essentially, as we already discussed, this first step kind of gives us the sense that infimum of gamma in I of I gamma is finite and well defined. That's the first step, you know, before we moving further, right? And as a matter of fact, you know, because I gamma is always greater than or equal to minus c, so, and surely infimum of gamma itself in I here, I of gamma is greater than or equals to minus c. Okay, so that's the first thing. The second thing is just nothing but just definition of infimum, you know, that we can find a sequence gamma k in admissible set A so that you have I of gamma k converging to the infimum value of I. Okay, so that's that, you know, that's the second step here. That's what we have. And then we're gonna use compactness result. So I'm skipping over it now. We're gonna get back to that eventually in this lecture. So so compactness result last time. It's gonna give us what we need. I mean, here, remember that you see we fixed the two endpoints, y and z, right? So last time, to have a compactness result, we have to have that gamma at a given point is bounded, but clearly here that, I mean, so clearly here that gamma k of A, let's say, is equals to A always. So, you know, gamma k of A is bounded. I mean, it's constant anyway. So what we need to show is that, you know, that's what I meant. We're going to skip over this now. That gamma k dot is uniformly integrable. Okay, so I asked you to think about this, but I'm not skipping it now. I mean, for now. It's not so hard, but it's, you know, it's telling us that there's something that we need. So what I'm gonna focus mostly on today is the weakly lower semi-continuity property. So meaning that if I have gamma k j converging to gamma uniformly and gamma k dot j converging weakly to gamma dot in L1, then I have this weakly lower semi-continuity. Okay, so weekly here means that it's for weekly conversion. Okay, so okay, I mean, this is also obvious to you, but let me make a clear remark. So if we have say gamma k dot j converging strongly to gamma strongly in L1, say, um, uh, then is then is I still have to be a bit careful, but it's easier, okay, to have such result, okay. But again, I mean, this is quite clear, but in the context of calculus of variation, it's really just typically the case that, you know, we only have gamma k dot j converge weakly to gamma dot in some norms. So this is weakly only. Okay. So typically a calculus of variation. Why? Because this is a step that we use compactness or weak compactness, whatever that means, and you know, there's often no ways for us to really get strong conversion at this point. Okay, so I recall quickly the assumption here, the conditions. So L is in C1, L dVL is bounded uniformly continuous if V is bounded. Okay, maybe here, let me recall here that L is LXV and dVL is also dVLXV. So they are L dVL bounded uniformly continuous in the whole Rn. So in X it's everywhere, but in V we only assume that it's bounded uniformly continuous for each of the velocity bounded by R. Okay, and to prove um, property, we only need to assume that V maps to LXV is convex. We don't yet need uh, uniform convexity or something like that here. What is important here is that we, besides the convexity, which is important, we also need the fact that it's so we really need those two properties. Those two properties are the most important ones. So most important ones convexity together with superlinearity. Okay. So as I said, I strongly believe that in the literatures there are counterexamples where L is only having linear growth. Again, check me, search the literature. For example, John Ball has some papers on that and stuff like that. There are some very interesting examples and counterexamples in calculus of variations, right? Um, so so I said we don't yet assume uniform convexity here. So we already proved last time very quickly the lower bound because L is superlinear, so it's bounded from below by a constant. So you can see the action functional is bounded from below by minus C times B minus A, no big deal. So one is whole, one host, 2 and 3 whole as well. So 2 is obvious, 3, I mean 3 here as well, this 3 as well here needs some justifications, but that's for later, okay? So now, I state the theorem here. This is our main focus today. So our main focus for today, that again, let me repeat, this is sort of the weekly, I think lower, what I said, there's a typo. It's not lower, but weekly lower semi-continuity. Again, and this is a keyword in calculus of variation. I mean, once you see it's done here, in this manner, we are doing it in pretty much a fairly general setting, or I would say that in our framework is the most general setting. So whenever you see this keyword, you can see, I mean, the way it's being done. Okay, so what I can say is that, you know, the proof today is pretty interesting. It's a bit technical, but it's pretty interesting. Okay, so okay, so let's do it. So let's do the proof. What do we have? I mean, so the first case, the easy case is that if lim inf of I of gamma k for k goes to infinity equals to plus infinity, then we are done, right? There's nothing to prove because, you know, it's already automatically greater than equals to I of gamma on the right hand side. So so we only need to consider case number 2, at which we have lim inf as k goes to infinity of I gamma k equals to a constant c in R. And in fact, you know, by extracting a subsequence and renaming it, just throw away things, we can say that we can assume that lim as k goes to infinity of I gamma k equals to c. Okay, without loss of generality. Okay, and then also without even further loss of generality, we can assume that not only it's converging to c, but you have c minus 1 is less than equals to I gamma k less than equals to c plus 1 by taking k large enough, and then you have I gamma k converging to c. Again, I'm just I'm just putting us to this setting so that everything is easier, simpler, I guess. And also, I mean, last time you guys asked a great question about the fact that once we have you know, uniform integrability and stuff like that, and once you have gamma or gamma k is bounded as a point, and it's bounded everywhere. So that was a great question, and that helps me a lot that I don't have to repeat it here. So moreover, we can also assume that gamma k and L infinity and gamma and L infinity are bounded. Okay, so actually I should add it here that also that we assume that gamma k in L infinity and gamma in L infinity about it. Okay, so that's the our setting. We have done certain reductions first to um, you know to get to this setting. Okay, so what's the scenario? So let me say it right away, the scenario, before we move on to the technicality. So the strategy is that we have I gamma k equals integral from a to b L of gamma k s gamma dot of k s ds. Okay, so this is the action functional. I need to use convexity, so I need to use convexity and superlinearity. Okay. So to demonstrate the strategy to you guys, let me consider this the easier case first. So easier case to demonstrate the key idea. A key idea is assuming, you know, this is not that, but you know, when I'm demonstrating the key idea, I'm assuming that L doesn't depend on X, so it's homogeneous in X. So L doesn't depend on X. Okay, so if this is the case, then things gonna be easier. And you know, if we see it here, then I guess that we can see it for the other problem, and you can see why do I need this technical lemma and stuff like that. Okay, So if this is the case, then here's how I do it. So I'm gonna use the fact that this is L of gamma k, and you see that by convexity gives that L of gamma k dot s is greater than equals to L of gamma s dot plus dvl gamma dot s dot product with gamma k dot s minus gamma dot s. Okay. So, if there's no spatial dependence, if there's no x dependent, then the problem becomes rather easy. I'm just using convexity here. I'm kicking gamma k dot here to gamma dot. By doing so, I have to take into account the supporting hyperplane, which is dv here dot with gamma k dot minus gamma s dot. Okay, so that's the thing. Um, Now, oops, this is I believe this is not a good color. Um, maybe this, I don't know. Okay. So if you observe this a little bit, what you see is that this one is good already, right? It's what we need to get to the limit. um, this one is in our infinity, right? Uh, let's see. Oh, okay, not quite. I have to be careful. Okay, so nearly. Okay, well, if gamma dot is bounded, then yes, it's in L infinity. But if gamma dot is not yet bounded, then nearly, right? I can, like use certain cutoff technique just to take gamma dot less than equals to some big number m and let m goes to infinity. So it's nearly in L infinity, not quite. Okay, but if this one is in L infinity, then it's good, right? Because I have weak conversion here. With conversions here, right? So if dvl of gamma dot is in L infinity, again, this is not quite, I'm assuming a lot here, then we are done, right? Done as, the right hand side, I can see that limit as k goes to infinity of integral uh, from a to b of dvl gamma dot with gamma dot k minus gamma dot s equals to 0, right? Because of weak conversion. Again, I have to assume that this is in L infinity. It's not quite, but then from here that we can deduce right away that lim inf at k goes to infinity integral the action functional of gamma k is greater than equals to the action functional of gamma, right? And we are done. Okay. However, this comes with two big assumptions. The first assumption was that I don't have spatial dependence. I don't have gamma k in the variable. The second one was that I have to assume that dvl of gamma dot is in L infinity. This is a little bit technical. It can be fixed. Okay, that's not a big deal. Uh, but in general, again, let me go with the remark and then I'll go back to the actual proof. So remark, in general, if we do it for L of gamma k dot naively, so if you have that, you have L of gamma k dot here, this is going to be greater than L of gamma k gamma dot plus dv of L of gamma k gamma dot product with gamma k dot minus gamma dot. Okay. So in general, if I do it naively, I would have that, right? But then, I mean, if you look into this term, This is not a fixed L infinity vector field anymore, right? It's changing with respect to gamma k, and this is not easy to handle, not easy to be handled. So this is changing in k. So that's why I have to be careful. If I have quick conversion in LP for p greater than 1, then it's easier to handle this problem. As I said, you can check in the appendix of my book. I did it for L2, and in L2 it's really quick. It's much easier. But here, if it's changing in k, and if it's not fixed, if it's not in L infinity, then I would be in trouble. So that's why I have to handle. So this means that we need to handle x dependence carefully. Okay. So that's why it comes with all those lemma. Okay. So now let me state the lemma, and we go with that. So you fix k and epsilon, and we say that there's a delta, so that if v is less than k, if v itself is less than k, and for all x, y in Rn with x minus y in the distance of delta, then we have this bound that we have Ly of w is greater than equals to the right hand side. The right hand side is Lxv plus dv of Lxv, dot product with w minus v minus some error term. The error term is okay. I mean, if there's certain error term, that's fine. So what is remarkable here is that this is correct for all w in Rn. Okay, so this is for all. So this is one key point. It's just not just correct for some w near v or something like that, but it's correct for all w in Rn. The second point that is remarkable here is that you see I'm using convexity in a smart way. I'm not just using convexity like naively like what I put down here for the L gamma k dot. But what I'm using convexity here is that you see that I'm putting the x lot here. So x here instead of y. Okay. Let me try to zoom it in. So you see I'm putting x instead of y because if I put y there, then I would have to be careful because it's changing, right? So what I'm doing is that although I'm comparing Lyw with things, but I'm comparing it with Lxv and then dv of Lxv. So x is then being fixed later on. Okay, so that's the point. Although it looks a very technical lemma, but it is quite important. Okay. So what do I have here? So you see that by convexity, if you do Lxw, then it's easy. So Lxw is greater than Lxv plus dv of Lxv dot product with w minus v. That's fine, right? Because we are doing it for Lxw. Now, as I said, what we need to do is Lyw, not Lxw, right? So there's a difference between the two. If w were bounded, right? If w were bounded, then we would able to use the uniform continuity of L in Rn cross B 0 R to conclude, right? But to compare Lxw and Lyw, this is for all w, okay? Okay, maybe let me put a little box here. So clearly we need to compare Lxw and Lyw. This is not just for W bounded, but we need to compare that for all W in Rn. And if W goes to infinity, there's the length of W goes to infinity. There's no guarantee that this even if X is close to Y, there's no warranty that LXW is close to LYW, right? So that's just a little glitch, a little technicality. However, what serves the day is the superlinearity of L. Okay. So what did I say? So the right hand side of this thing above here, because V is bounded and L and dVL is bounded, so the right hand side of the thing above is bounded by a constant times 1 plus W, right? Because LXV is bounded, V is bounded. Uh, dV of LXV is bounded and it's grow with at most the linear speed in W. Okay, so that's the key.
Can I
Now
ask a
we
question
have,
about that?
yeah,
So
sure.
I guess the first step made sense to me in that inequality.
Uh-huh.
Replace the L and the dV with C. But then how do we get the second inequality?
uh because V is bounded, right? uh, from okay, the second inequality is the fact that we are just using the triangle inequality that W minus V is less than equals to W plus V,
Right.
and less than equals to W plus K. Okay.
Right, but shouldn't there be some extra constants? You have C times this extra, you have 1 plus absolute value
Sure,
of
sure, sure. But,
W.
but yeah, well, good point. Thanks. But I mean, remember that my constant C is changing not just line by line, but inequality by inequality. So by the second inequality, C is something bigger. That
Okay.
Yeah. So this
Right.
is sure. I mean, this is just it's just to avoid certain bookkeepings, so that we have to uh, bookkeeping all the dependents. Actually, sometimes it's very important to know what's the real dependence. But here, I'm being lazy. So
Okay.
you're absolutely right. The next C should be like C plus K or something like that. But I'm just putting it to be the new C. Okay. Yeah. Thanks a lot. That's really that exactly the point. Okay. And now you see that I'm using superlinearity here in a very strong way because I'm using the fact that LXW is growing superlinearly in W, right? So what we are saying here is that actually, although we have to deal with OW in Rn, but it actually doesn't matter if the length of W is large enough, right? Because we can find C1 so that Lx of W is greater than C times 2 plus W and greater than the right hand side in case that W is large enough. Okay, so that's the point. It's growing superlinearly. The right hand side only grows linearly in W. So if you are having W large enough, you should, the left hand side should already be bigger. And this is very important because it allows us to ignore the big regime that we can just host automatically if W is greater than equals to C1. So what it helps us to reduce to is only that we consider W, the length is less than equals to C1, right? And you see that if the length is less than C1, then we are using now the fact that it's uniformly continuous in here. So you can just do the actual epsilon delta approach, you know, um, uh, you know, maybe what I think I should add here that for x minus y less than delta and w less than C1, right? Just to make sure that we are correct. So we are done. So we have left hand side this one and it's greater than that and greater than the right hand side. And you see that we have to sacrifice a little bit epsilon here, but the take home message for us is that we have LYW is greater than equals to LXV. I'm switching everything to X, and this X plays a key role because of what I just explained to you. The fixed X here gonna plays a key role. that I don't have to deal with the changing y later on. Okay. Right. So thanks a lot for the question, and you know, this actually this is actually very important, and you see that many times in calculus variation people try to deal with a simpler setting, and I also chose to do it many times. If I have a priori estimates, if I have time later on, I will explain to you what do I mean by a priori estimates. And if I have that, I can choose to do in a simpler way. And here, if I don't have any a priori estimate, I have to deal with the most general setting, and sometimes it's a little bit you know, technical, but I hope that I have explained to you the key point. All right, so now we are ready to deal with our theorem. What do I have to do here? So yes, we have gamma is bounded. I mean, we said it earlier, we have gamma is bounded. Gamma dot is not yet bounded, you know, right? So this is the normal technique of cutoffs, you know. The only thing we can do is that we define u lambda to be the set that gamma dot is bounded by lambda. And the idea, the normal, the actual techniques of using cutoff in measure theory or in analysis or PD is always that, you know, we cut it off at the level lambda and we let lambda goes to infinity to capture everything, right? So if lambda goes to infinity, then u lambda goes to AB, again, up to a set of zero measure, you know, but that's fine. Okay. So in u lambda, so I'm only considering u lambda here. So if you fix an epsilon, then there is a delta, so that this holds, right? This is exactly just our earlier lemma for all w in Rn, for x minus y less than delta, and for v less than lambda. Okay, what is this v less than lambda? You know, remember that v, okay, so v represents gamma dot s, right? So v less than lambda, meaning that gamma dot less than equals to lambda. Okay, so you see we are being really rigorous here, and we can't just assume that, you know, here early in these steps I assume that here, right, early in these steps I assume that dv is in L gamma dot, dv L gamma dot is in L infinity, and I said that this is sort of nearly, it's not really, and what we are doing it right here is that we are trying to make it correct. But I'm sorry, when I zoom out and zoom in, I'm confused with the position. Okay, so what we are trying to do here is that we are trying to make it correct by just considering in u lambda, and here is only for v less than equals to lambda. And surely, I mean, you can say that delta here depends on lambda and epsilon, right? I mean, you know, surely delta here depends on lambda, epsilon, and the uniform continuity of L. Okay, so depends on lots of parameter. We have to be careful. All right. Oh, there's a mistake with my L. Oh, this is weird. Okay. I don't know how does it jump like that. Okay, so let me correct it. Okay, I'm sorry. So all right, so we pick k large enough, we have gamma k converging uniformly to gamma. So if you pick k large enough, you're gonna have gamma k minus gamma is gonna be L infinity norm less than delta. So you can apply exactly the earlier claim, the earlier lemma, to have this. So you have L of gamma k dot is going to be greater than equals to L of gamma dot. You see, you know, Okay, let me do this and then I'll come. Plus dv of L gamma gamma dot product with that and minus epsilon. Again, I have to pay minus epsilon. That doesn't matter. And this is only true for k large enough and for s in u lambda. It's not for all s, but only for s in u lambda. So, okay, let me zoom out here a little bit. You see that this step, this is better, right? Than the naive way. The naive way was that I do it for L of gamma k gamma dot and dv L of gamma k gamma dot, right? But that thing is changing, and okay, technically it's a little bit dangerous. Okay, so you see that what we are doing on the left hand side is better because in the gamma, here's gamma and gamma, which is already a fixed curve, so I don't have things running. Okay, so that's a key point. um, and you see that in okay, and you see that also here that in u lambda, you have dv of L gamma s gamma dot s is in L infinity of u lambda. Okay, because in u lambda, I mean gamma is itself bounded, but gamma dot is bounded in u lambda, right? So it's in L infinity. So when it's in L infinity, then we can apply exactly uh, the weak conversion result, and that's exactly what we are doing. So you see that I write I of gamma k is this integral only on u lambda, and this is a sort of remainder, right? So you have this is the remainder. Okay, let me say it right away that the remainder is not dangerous. The remainder is not dangerous because you have L is bounded from below, right? So the remainder is already greater than equals to minus C, right? Because L is bounded up from below by minus C times the measures of of the remainder set, right? So the measures of the remainder set is IV takes away U lambda, and this one goes to zero as lambda goes to plus infinity. So I mean that is you know fine. Hold on, I think I have a question in the chat. Is that left hand side instead of right hand side? Maybe it was a question a few minutes earlier. Hold on, let me. Sorry, sometime I didn't see the chat box. Where's the left hand side and right hand side? Now I'm totally confused. Is it here? Uh, if this is here, then I believe it's the right hand side. If it's not, then I'm sorry. I'll get back to you. I mean, once we are done with this time. Okay. All right. Anyway, I just claim that the remainder is it's vanishing as lambda goes to infinity. That's fine. And you see that we are using the inequality here. You have the integral on u lambda is greater than equals to the actions of L of gamma on u lambda plus this integral minus the it's not good. Okay, and then there are two terms, minus epsilon u lambda and minus c, that measures I just mentioned, and both of this goes away. Both of that vanish. As lambda and epsilon goes to zero in the correct order. So you see that, and also I'm being careful. I'm rewriting this one as the characteristic set of u lambda multiply this one, but this one is a bounded function. And when you take a bounded functions dot product with this thing, it goes to zero as okay. What is the order here? This one goes to zero as k goes to infinity first. Okay, so you have to take k goes to infinity first to omit this term. Okay, and after k goes to infinity, you take lambda goes to infinity, because if lambda goes to infinity, then you have this integral converging to integral from a to b L gamma dot ds. And when lambda goes to infinity, it doesn't matter. This one also goes away. And eventually epsilon goes to zero. Epsilon goes to zero to have this one goes to zero. So once you have done that, we are done. Okay. So we are done. Then with the proof that lim inf k goes to infinity of I of gamma k is greater than or equals to I gamma. Okay, so this is a very, I would say that what is really interesting to me is that this is quite a general setting. And the second one that is interesting is that to handle L of gamma k dot, we we need to be careful. So we need to be careful with the gamma ks lot, with gamma ks, and we use the convexity in a smart way, something like this: gamma dot plus dvl of gamma dot gamma k dot minus gamma dot minus epsilon. So we are switching it to gamma here instead of gamma k. So gamma here is better than gamma k. Okay, so that's a technical thing, but it's rather important. And final remark is that maybe, so if Lxv is greater than or equals to some small constant v square minus big constant, then the proof is much easier. So see appendix of my book. And also for the calculus of variation setting, I would say, I mean, this is also calculus of variation, but what I mean calculus of variation setting is that you should see Evans in chapter 8. I might be wrong about the chapter, but there, to handle this kind of things of dependence, there Evans also have to use the so-called Egorov theorem. It's a measure theory device, so that you got to be careful when you're dealing with what's the dependence is. Okay. Right. So any questions or things you want to discuss with me before we go back to, okay, my notes today is a little bit messy, I guess, but it's fine. Before we go back to the point that I need to show that gamma k is uniform integrable. So first of all, Jiwoong, did I answer your question or not? There was a question about left hand side and right hand side. Was it the one or was it not?
Yeah, in the yellow color.
This one you mean?
No, the above one.
The upper one.
Yeah,
The upper one.
so right below the proof.
Right.
RH.
What? Okay, I'm sorry.
I thought
Right
that would be.
Oh, the right hand side is less than, no, that's still the right hand side you, right? Because I mean, what I'm trying to do here is that I'm trying to control first this term.
Oh no, the
right.
In the right below the proof, there is one line colored by yellow.
This one, right hand side here.
Yeah. I thought
Yes.
that's LHS. I thought.
I thought that, okay, yes, but I think that that's exactly what I meant. So I was saying that the right hand side of this right hand side here, oops, I don't think this is a good one.
Oh, yeah. Then there is. Oh, sorry.
Yeah, so I'm trying to control the right hand side. What I'm saying is that, I'm sorry that my notes is a little bit messy today.
Uh,
I'm trying to
no,
control the right
everything
hand
is.
side. Yeah, no, it's because of my notes, I guess. The right hand side is going linearly in W, and the left hand side is growing super linearly in W.
Right.
So what we are saying is that we only need to control for W is being bounded by a C1, something like that.
Yeah.
Okay. Okay.
Thanks.
So thanks a lot for the questions, and right. So I found out that the zoom in, zoom out option is better for you guys, but sometimes it's hard to keep up with the order of the notes, whatever. Okay. So now, any other concerns? Okay. So I guess we have 1 minute or two. This is enough to prove that gamma k dot is uniformly integrable. Okay. And as I said, calculus conversion is a great subject actually. In my view, it's has still lots of mysteries and lots of open question. I guess some of them are actually very hard. Um, Here, proving gamma k is uniformly integrable, we need to use once more we need to use that L is super linear what linear in V. Um, Rather strongly, because you see that we have L of integral on AB of L gamma k dot ds is bounded, right? I mean, we just assume that it's already bounded between C minus 1 and C plus 1, right? Um, uh, so what's the point? How do we prove that it's uniformly integrable here? The fact of that is superlinear is that you find that for any, say, any constant k greater than 0, then there is ck greater than 0 such that you have L of xv is greater than equals to k times v minus ck. Okay. So it has linear growth at least k, and you have to subtract a big constant ck. It doesn't matter. Okay, but that's that. Then you write out, you use these formulations, right? So you have integral from a to b, k times gamma k dot minus ck ds is less than or equal to c plus 1 or something, and so that implies that you have k times integral from a to b gamma k dot ds is less than or equals to a big constant c. You switch ck. Okay, let's be careful. C plus ck. Okay. So I'm almost done. Bear with me for one last minute. So uh, what's the better way to write this one down? Give me 1 second. I'm trying to find a better way to write this one down to finish up the proof, because maybe a better way to write this one down is this. Okay, so you take integral on any set E gamma k dot minus ck. No, yeah, okay, this is better. ds is still less than a big constant c, right? Because the outside you can just put it on the right and okay, and if you then for a set E of measure less than equals to delta, what do you have? Okay, so what you have is that integral on E gamma dot k ds of k is less than equals to c plus ck times the measure of E, right? And this is c plus ck times delta. Okay, so what this gives you is that integral on E of gamma k dot ds is less than equals to c over k plus ck over k times delta. Remember that you can choose k so that c over k is less than epsilon over 2 a priori, right? You choose k big enough so that c over k is less than epsilon over 2. And then, here you choose delta so that once you fix k, then you have ck over k is a fixed number. So ck over k times delta less than epsilon over 2, then the whole thing is less than epsilon. So that gives you uniform integrability. Okay, so it's really beautiful. And we are using strongly the superlinearity here. Okay, so I'm going way over time today, but I hope that you bear with me on that. Okay, without further things, so let's end it today, and then I'll see you again on Friday. I'm sorry to go a bit over time, and I hope that everything is clear by now. Okay, so thanks a lot, guys. See you on Friday. Bye. Thank you.